So we're going to see now a very popular algorithm for biomedical signal processing is the Pan-Tompkins algorithm. So you could see, this technique could be used for real-time QRS detection in the ECG signals. So this presentation is based on the original article written by the authors Pan and Tompkins in the year 1985, which was published in IEEE Transactions on Biomedical Engineering. I highly recommend that you go through this paper because it contains very important details about how to involve various filtering and schemes for thresholding so that we could detect QRS complexes in a more robust way. This technique has also found a lot of practical applications in various biomedical products. So this work is a good example of a solid research and a very good innovation. So you can get the details from this work as well as from the lab experiments that you would be doing in the related topic. So what are the key features of the Pan-Tompkins technique? It's a QRS detection algorithm, and in an ECG complex, we have three prominent waves: the P wave, the QRS wave, and the T wave. So this algorithm specifically focuses on QRS detection because detecting QRS peaks could lead to the understanding of the heart dynamics, heart rhythm, and also the variabilities that arises in the heart rate. It has a series of filters, and the filters are originally designed for a sampling frequency of 200 Hertz. It's quite interesting. The original work in 1985 was designed to be implemented in a microprocessor. So it was using a very low-level language in assembly. And important aspect is that it's basically how do we analyze the slope, the amplitude, and width of QRS complexes. And it does use a series of very simple methods that we will see in the next block diagram. So this is a block diagram I would like to point out. An ECG signal would go through a bandpass filter. The idea of the bandpass filter is essentially to enhance the QRS complex in the ECG. Then it goes through a differentiation process, followed by a squaring operation. Then the final filtering is a moving average or moving window filtering. Followed by that, we could involve some logic and some algorithms to do the beat detection or the QRS complex detection, the number of QRS complexes, by using various thresholding methods. And the method that's recommended in the paper is an adaptive thresholding method along with search pack, so that we make sure we do a robust detection and estimation of QRS complexes. So this diagram gives the spectral behavior or the frequency behavior of an ECG signal and the associated components. So to start with, you could see the muscle noise is a very, very low frequency activity, and it typically occupies a very low power. And sometimes the power could extend to the entire frequency of interest. So here the frequency of interest for the given ECG signal is below 40 Hertz. So the ECG signal, the bandwidth occupied is around 40 Hertz. In the low frequency, there is also the motion artifact. So the motion artifact is typically below, we could see around 7 Hertz or 8 Hertz frequency. It tends to peak around 4 Hertz. Then you have the QRS complex. Okay, so the QRS complex bandwidth occupies from approximately from 3 hertz to almost 40 hertz. Okay. And it has a significant power. Okay, so this is the QRS complex's spectral behavior. So this is just a template. This is one scenario of how the different components are reflected in a ECG signal. The muscle noise normally comes also due to respiration. The motion artifact comes obviously because of movement. And the frequency of interest here is a QRS complex. Okay? And the ECG signal occupies the complete bandwidth of around 40 hertz. Okay? So that's kind of the idea here. Now, how do we go about in applying the various filtering concepts that you have seen so far for a practical real-world application is a key next step. So the bandpass filter, which is the very first step in the QRS detection process, allows us to basically take care of the muscle noise. It eliminates the 60 hertz interference automatically because it only goes up to a bandwidth that's less than 60 hertz. So 60 hertz frequency is gone. The baseline wander is also gone, and the T wave are reduced. So that's the main intention of the bandpass filter, is to basically do a reduction or a removal of these 4 major things: the muscle noise, the 60 hertz interference, the baseline wander, and the T wave interference. The reason I use the word reduction is that, as you know, I mean, many times we won't be able to design an ideal filter because there's always a roll-off that's involved. We don't get sharp cutoffs. So it's possible certain frequency components might be leaked into the system. Okay? And it also ensures that we are maximizing the performance of the filter in the range of 5 to 15 hertz, which really enhances the QRS complex. Okay? So the frequency of interest in this block diagram is between 5 to 15 hertz. This is a digital filter, and we will get to see the difference equation and the transfer function of those digital filters very soon. But the most important fact that you will realize as we go along is that the filters do have coefficients, as we have seen before, but the coefficients in case of a Pan-Tompkins algorithm tends to take integer values. Okay? And there are various advantages of having the coefficients to be integer. It really allows us to do a real-time implementation, even in a very low computational resources such as a microprocessor. It's fast. In other words, the latency is quite low. And also, it has the advantages of basically, getting a better representation of the filter in terms of the pole diagram configuration of the visualization aspect as well. The one difficulty with going with the integer coefficients is that we cannot really design a bandpass filter for the given cutoff 5 to 15 hertz directly. Okay? Because if you want the filter coefficients to have an integer value, it's quite hard to design a bandpass filter directly to meet those specifications. But we can mimic a bandpass filter by cascading a low-pass filter and a high-pass filter. Okay? So cascading means adding the 2 filters. I would add 2 filters, a low-pass filter and a high-pass filter, to synthesize or mimic a bandpass filter here. Okay? So the low-pass filter will ensure that the cutoff above that frequency is not passed, and the high-pass filter will ensure the cutoff frequency and below are removed or reduced. Okay? So this cascading operations gives the functionality of a bandpass filter. So it's easier to have integer filter coefficients for low-pass and high-pass design. So that's the way to go about in designing the bandpass filter. By the way, all those filters that I'm talking were designed by the original authors of this work, who are Dr. Span and Tompkins. So in the bandpass filter design, we essentially start with a low-pass filter, and the low-pass filter aspect of it is given, the transfer function is given here. And if you look into this more carefully, this low-pass filter is pretty much a very neat filter with numerator and denominator polynomials, and definitely this is an IAR low-pass filter. But if I look into the coefficients of the numerator and the denominator polynomial, they carry integer values. Okay, in this specific case, it happens to carry either plus or minus 1 values. Okay. So this is an important aspect to keep in mind. And this low-pass filter essentially gives a cutoff frequency of 11 hertz here, and it introduces a delay of around 25 milliseconds or 5 samples if you assume the sampling frequency to be 200 hertz. Okay. And if you also see the kind of how this transfer function looks like, it also kind of represents some form of a moving average. And we have seen before a moving average operation, any averaging operation or an integration operation is a kind of a low pass filtering operation. It tends to remove the high frequency components. And in terms of the pole zero diagram, this is how it looks like for the low pass filter design for the first stage of the Pan-Tompkins filtering process. And the location of the zeros are shown to you, and also the location of the poles are shown to you by the cross symbol. And this is the frequency response of the low-pass filter, which has both the magnitude response and the phase response. If you see the magnitude response of the filter, it shows the low-pass behavior of the filter design. And the other advantage is also that within that frequency range of interest, the phase response behaves in a linear way. So it's a linear phase low-pass IAR filter here. Now, in terms of the high-pass filter, the high-pass filter design, also we have gone through the process to ensure the high-pass filter design also have integer coefficients. So it happens that the high-pass filter's transfer function is given by this notation here, which is z power minus 16 minus the transfer function of the low-pass filter. So what it is basically doing is that it's subtracting from an all-pass filter, an all-pass filter that passes all frequencies. The all-pass filter is subtracted with a low-pass filter, which is HLP. Then you get the high-pass equivalent. Okay, so that's a trick they have done in designing the high-pass equivalent of it. So essentially, that translates into a block diagram representation like what's shown there. So the filter transfer function for the high-pass filter that is used in the first stage of the Pan-Tompkins is this notation, and the low-pass filter's transfer function is given here. Okay? And low-pass filter, just like how we saw before, would be seen as a moving average operation. So this is essentially a 32-point moving average filter that gets subtracted from the all-pass filter to give you the high-pass equivalent of it. Okay. So this filter introduces a slight delay of 80 milliseconds when you assume the sampling frequency to be again 200 hertz. So this is the configuration, the pole zero configuration of this high-pass filter design. If you see this representation, it essentially has a lot of zeros, and also it has poles right at the origin here. The poles at the origin, I mean, they don't do anything to the stability. They make sure the filters are stable. Just to point out, there is also poles on the unit circle, for example, here. And that was intentional. So what they have done is that they have ensured by putting certain poles right on the spot on the unit circle, they're not doing anything to the stability. All it's doing is that it's a mathematical convenience where the zeros are getting cancelled. Okay, so the zeros and the poles cancel each other, so it doesn't have any impact on the stability of the filter. Okay, so again, this is a very neat design. The reason they have to come with this kind of a configuration is that to essentially make sure the filter coefficients that we just saw before are all integer values. So this is how the high-pass filter's magnitude response looks like, and you can essentially see that it starts to pass any frequency that's above maybe around 8 hertz. Okay, so it's having almost a unity gain above 8 hertz, and also the phase response is linear within the frequency range of interest. Okay. Now, the bandpass filter is essentially the cascading of the two filters that we just saw, the low pass and the high pass. Cascading is just putting one filter next to each other as a series combination. And when you do the series combination, and then you can essentially get the cutoff frequency that you're looking at. So the pass band would be 5 to 15 hertz range. And in this range, essentially it maximizes the QRS wave. This frequency range also attenuates the P and T waves because they tend to be outside this 5 to 15 hertz frequency range of interest. They also remove high frequency artifacts, especially the power line interference. So there is really no need here to use a notch filter to remove the 60 hertz or the 50 hertz interference that's typically seen in other biomedical signal processing applications. Okay. So now, after the first stage of the filtering operation, the ECG signal is filtered and only the 5 to 15 hertz frequency is enhanced because that's the frequency that matches the QRS complex. Okay. So the cascading operation, which we just discussed, would have a frequency response behavior like this, and you can easily see that this is the frequency of interest that is really been looked into, and really very strong performance in the range of 5 to 15 hertz. Then it slowly starts to attenuate after 15 hertz, but it really does a good job in the range of 5 to 15 hertz. And no doubt the filter is also behaving in a linear phase. So this would be the joint low pass and high pass filters pole zero diagram. And you could see this has a lot of zeros in the system, and there are a few poles, but the poles are not really doing damage to the filter. It's a stable filter. And again, the cascaded filter has also given coefficients that tends to be of integer values. Now, what would happen in reality with this kind of a bandpass filter as a first stage of the QRS complex is that when this ECG signal is passed through, you could see it really, the output of the bandpass filter, which is a cascade of the low pass and high pass, has increased the QRS complex, and it has really attenuated the P and the T waves. So the T wave, which was dominant, and also P wave, which was slightly dominant in the original ECG signal, are attenuated. So that's the idea behind the first stage of the processing. Now, the second stage in the Pan-Tompkins algorithm is the derivative filter. And you have seen this derivative operation before, including in one of the labs. The idea of the derivative filter is really to enhance certain frequencies. So it's kind of a high-pass filtering operation. And typically, mathematically speaking, a derivative filter is one that really enhances the slope in the signal, okay? Because the slope in a signal, in a time domain signal, corresponds to some kind of a relatively high frequency activity, and that really gets enhanced through the derivative operation. And the Pan-Tompkins, they've used a 5-point derivative operator, and that has given the filter transfer function to have this kind of a notation. Again, if you look very closely into the difference equation, which is this equation underneath, you could see the coefficients, and you can also even get the coefficients by looking at the transfer function, tends to have integer values. So they have a value of 2, 1, and -1 and -2. Okay, so that's kind of a all are integer coefficients. Okay. So derivative filters is a kind of a difference operation. And in this case, it happens that it introduces a delay of around 10 milliseconds or 2 samples, which is quite insignificant considering the sampling frequency here is 200 hertz. Okay, so it's a really instantaneous operation that's been done on the second stage of the Pan-Tompkins algorithm. So this is how the filter response looks like. The magnitude response has really done a good job in basically enhancing the QRS complex's bandwidth, and also it has provided a phase response that is desirable. Okay. And if you were to see the plot of this one in the scale of what's called the log-log plot, typically in the previous things we have seen the plot to be a linear x-axis and a logarithmic y-axis. Here, just to show, when we have a logarithmic x-axis and logarithmic y-axis, which is the magnitude in dB, you would see the frequency response of this derivative filter is linear. Okay? It's linear, so it's basically giving the idea that it's really doing a very good job in terms of acting like a high-pass filter, because as the frequency is increasing on the x-axis with a logarithmic scale, you see its response is also increasing linearly. Okay. Now, the combination of the bandpass filter and the derivative filter, which is stage 1 and stage 2, the response is shown there, and it's all easily derivable. Okay? Because you see, when the filters are put in cascade, the impulse response also gets added. So it goes back into the basic concepts you would have seen in signals and system. By adding filters in series or in parallel, what happens to the impulse response and transfer function? That's exactly what we are noticing. Okay? So here, yes, the bandpass filter was cascaded with low pass and high pass. Then we had a derivative filter. So basically here, 3 digital filters are in series or in cascade. Okay? And when we put all of them together, we can always get even one transfer function that combines all the 3 filters, because they're all additive operations. It's simple linear operation. Okay? So that's what we are noticing here. When we add all of them, it could be seen as just one filter, which is doing a low pass, high pass, followed by a derivative operation. And that's how the frequency response and the phase response looks like. Similar to what we have seen before, this is a pole 0 diagram of what we just discussed. Now, in terms of the waveform, the original ECG signal, when it passes through both the bandpass and the derivative operation, you could notice that this QRS peak is starting to be enhanced even further because of the derivative operation. And even if you don't go through any of the filtering, even just seeing this as a mathematical operation, when we do a differentiation dy by dt on this original ECG signal, obviously the dy by dt, the derivative operator, would be acting more on signals which are steeper, which are sharp morphology. And it might do the same impact on the T wave, but this T wave, just because of what we did with the original first stage of bandpass filtering, has attenuated the T wave. So the derivative filter right now is only operating on the QRS complex, and the T wave is basically diminished, attenuated. It's just because of the help that we got from the very first stage of the bandpass filtering. So that's why the bandpass filtering has allowed us to do, is that it has really zoomed into the QRS complex. And when we zoom into the QRS complex, then when we apply the derivative operator, it's really enhancing the QRS complex even further. Now, the next operation is that, obviously it's a smart operation, is that the idea here is to pick the QRS complex, because when you pick the QRS complex, it relates directly to the heartbeat. The QRS complex corresponds to ventricular contraction. Each time your ventricles are contracting, it generates the heartbeat, and that's how you get the beats per minute measure. Okay? So the next step followed by the derivative operation is the squaring operation. And the squaring operation is very simple. You do a sample by sample squaring. When we do the squaring operation, what happens is that it's a simple non-linear operation. Okay, if a quantity is larger, it gets even larger, and if the quantity is very small, it gets smaller. Okay, so this non-linear operation, it's a simple non-linear squaring. The simple non-linear operation has really allowed us to enhance the QRS complexes further, and you're pretty much starting to see almost a flat line that was corresponding to the P waves and the T waves. Okay? So it's a very simple but a smart operation that really has allowed us to amplify the output that we got from the derivative filter. Okay. So the fourth stage, or essentially the third stage, like the first stage, if you could see as a bandpass filter, the second stage is a derivative filter, and the third stage, it's just a operation, a squaring operation, followed by another filter, which is a moving average or moving window filter. We have seen this before, and why would need this moving average after a squaring operation is essentially it does MA moving average does a low pass filtering is essentially to ensure any small wiggles that might be still remaining as part of the T wave or the P wave or even high frequency noise. Okay, so the examples, the graphs which we have seen before are cases which are pretty much noiseless, or in other words, they had a very high signal to noise ratio. But in a noisy ECG, it's possible that we might end up in having smaller oscillations here. And how do we really suppress those smaller oscillations is what exactly the moving average filtering is doing. So it's ensuring that such residual high frequency noise is smoothened out through a final stage of moving average or a low pass filtering operation. Okay. So here, in this algorithm, window width n is chosen to be 30 samples. That's the original design by the authors Pan and Tompkins, and it corresponds to a delay of 150 milliseconds. Essentially, they wanted to cover the QRS complex when they're doing the moving average. Okay. So what happens is that if you select this window length to be large, then there is a possibility that you might be crossing into the territory of other waves if there are some residual components present, like the T wave. On the other hand, if your window was too small, then it might be operating within the QRS complex, then you might get some false positive in terms of the peaks detection. Okay, so the window length has to be optimally selected, and that's why for this particular design, they've selected 150 milliseconds, and when you consider sampling frequency to be 200 hertz, it's 30 samples. So this would be the output of a moving average filter. So if the ECG signal is going through the Pan-Tompkins stages, so it goes through a bandpass filter to start with, then next stage is a derivative filter, then it goes through a squaring operation, and after the squaring operation, you do a moving average operation. Okay. And this waveform would be the output of the moving average operation. And if you could see what was shown more like a triangular and more like a smooth Hanning type of window aspects of the original ECG corresponding to the different contractions and repolarizations have been all converted into a pulse which looks like this. Okay, so that's exactly the output you will get after passing through the Pan-Tompkins technique. So this is the output of the moving average filter, and from here you could measure, if you know the window length, which we know here, it was window length of the moving average filter was 30 samples, which we know, or 150 milliseconds, which was just discussed. Once you know the window length, you can definitely measure the QS, okay, because that's the other thing that's present in the output of the moving average window. In other words, the output of the moving average window, the length of that single pulse would be a QRS complex width plus the width of the window. Okay. So once we know the width of the window, if I subtract that, then I can get basically the duration of the QRS pulse. Okay. So in addition to telling, okay, there is a presence of a QRS pulse, which is beat detection, it's also giving us the length of the QRS pulse duration. That's important because in a lot of clinical context, the duration of the QRS complex plays a significant role in understanding what's happening during arrhythmia or in cases of premature ventricular contraction and a lot of disorders. So in addition to detecting QRS pulse, knowing the width is essential, and that's exactly the output of the moving average filter is allowing us to do. So it also gives the width of the QRS complex. So this would be the basically the moving average filter, the filter which we just discussed. Pole zero diagram will look like, and this is its magnitude and phase response. And if I were to go through the steps which we discussed in a given practical application, so this is the ECG signal we start with, and the example which we have taken is not really that noisy. It does have a very good signal to noise ratio. So this would be the output that we would get after the first stage, which is a bandpass filtering, which involves a cascading of low pass and high pass. Then in the next stage, when we do a derivative operation, which is some kind of a high pass filtering operation, we see the peaks are getting further amplified, whereas the smaller peaks are getting starting to disappear. Okay. Obviously, to enhance this further, we can do a squaring operation. When we do the squaring operation in this panel as shown, we could see that it's really starting to highlight the QRS complex. After this, when we pass through the moving average operation or moving integration, and that's what the original authors called, because averaging is equivalent to integration operation. So if you do that, and then obviously we are picking up this output. Two pulses are shown. So basically, there are two QRS complexes or two R peaks for that matter. And it also allows us to get the width of the QRS complex, just like how we discussed before, because this width that we can measure would also give us a reliable and robust estimate of the QRS pulse width. Okay? So that's kind of the graphical illustration of the various things that we have seen. Now the point comes, okay, now how would I make my algorithm followed by the moving average to detect two peaks? Okay, so you could, yes, apply a simple threshold like this, and you can count like whether your signal has crossed this threshold and use some kind of a logic to say there are only two peaks. Okay, because for example, in this case, the moment it crosses a threshold, which we picked a fixed threshold, then any point above this line, it will start to count. So when it's counting it, it's counting for a while, then it starts to have no counts because nothing is crossing this line after this. Obviously, there are no peaks being detected. Then again, it starts to count. Okay? So those counter values obviously are having some higher numbers, but eventually we need to say there are only two peaks. So you need to use some kind of a logic and thresholding to make it work in a way that you wanted the peaks to be detected in a robust way. So fixed thresholding is one easy way to go around, but the authors have proposed an adaptive thresholding method, which we will see very quickly, to make sure that we are really counting the number of peaks without any false positives. Okay? So this is an example where you could see that there could be some error if there are very strong dominant peaks that might come because of a pathological process. Okay, so this is an unfiltered ECG where you will see a premature beat that's been introduced, but this algorithm is pretty sensitive, and what it does is that eventually it tells, okay, that false peak is also being picked up. Okay, so this is output of the final moving average windowing operation. But you could apply this thresholding scheme that I just mentioned and use some logic to basically tell, okay, it's quite impossible from the heart mechanism that there are two peaks which are pretty close to each other. Okay? It's quite impossible in a normal heartbeat. So you could turn around the output of this moving average filter and use suitable logic and basically indicate there is something wrong with the ECG. There's an abnormality happening in the ECG. Okay, so this is kind of the very first step towards making the computers recognize, oh, the ECG signal we are dealing seems to be abnormal. Okay. So it's starting to learn through an algorithmic view that things are not going in the right direction. Okay. So that's an important step, because it's known that adjacent beats, adjacent QRS complexes should be of a certain width. Okay, they should go through a certain duration. It happens that this second peak has appeared quite rapidly after the first beat, and that's pointing to us from an algorithmic perspective that there is something wrong. Okay, just to point out that how we can turn around these various outputs in a way that you want it to adapt to the application in hand. Okay? So in addition to measuring the number of beats, which is measuring the number of QRS complexes, measuring the width of the QRS pulse, we can also see the measurement of arrhythmia or appearances of instant and rapid beats next to each other. Okay? Now, the final step with the Pan-Tompkins after the moving average, we talked about thresholding. Essentially, yeah, you can use a combination of adaptive thresholding and search back techniques to basically ensure that you have done a very high, robust estimate of the direction of the QRS complexes. Okay, so the adaptive thresholding is essentially the way the original authors have recommended. It's just because this adaptive thresholding allows us to fit the variabilities that each and every human subject brings into the heart rate dynamics. Okay. It's not like one size fits all formula. I mean, yes, up to the moving average, we can use some fixed filtering operations, but after that, we have to use some adaptivity so that it's tailored according to the subjects or the patients. Okay, so that's exactly the adaptive thresholding is doing. They've proposed various thresholding schemes, and to me, this might constitute, as I just indicated, as a very first level of machine learning. Okay? Because they're asking the computer to understand this thresholding in a way that's adapted to individuals. So this way, when we're tracking the individual's ECG over time, longitudinally over longer time frame, we can see whether there is any deviation from the original baseline values. Okay? That's just one example of it. Okay? So the thresholding scheme, which is done as per an algorithm, they provided that algorithm in the paper, and I would really like you to go through that in detail if you want. It will also give you some ideas for your own projects. Could be modified. I mean, that's open for a lot of innovation in that area of thresholding, and essentially with their own thresholding which they've developed, and they applied on a very popular data set which is available in PhysioNet, and they got an accuracy of 99.3% in identifying QRS complexes, and the technique is also fully real time. Okay, fully real time, because as we have seen, very little delay has been introduced by the various filters. 99.3% accuracy, where this algorithm, which is automated, matches with what was a labeling that was provided by technicians and cardiologists in annotating those ECG waveforms they've tested with. Okay. So it's a very high accuracy rate, very robust. They've also tried with various abnormal conditions of ECG, and the paper covers all those details. Okay, so this is a great result. Even in 1985, they got fantastic results with that. And since then, this algorithm has been taken and applied in various other applications with regards to beat detection. I mean, people have also modified this to do P-wave detection, also modified this to do T-wave detection. It's just, in the initial stages, instead of focusing on 5 to 15 hertz, if you focus on other frequency bands, then you can even detect P-wave and T-wave. And as some of you might know, detecting P-wave has a serious application in domains like atrial fibrillation, okay, because it corresponds to atrial depolarization, the P-wave. So you could use a suitable bandpass filter to take out the P-wave first and go through the other subsequent steps we just saw for QRS complexes, the same methodology, use your own thresholding scheme, and you can do a reliable estimate of P waves as well. Okay? So modifications and innovations is up to you. I mean, so far we have seen a very nice systems view of how different filtering have come together in enabling this to happen. And most importantly, the reason why we are happy about this technique is also that it has a hardware implementation associated with it. And because the filter coefficients which we saw were all integer values, it allows us to do hardware implementation, and it also gives us fantastic real-time utility and nothing to be worried about the stability of the filter, because there are really no poles that are outside the unit circle. Okay? Yes, they have kind of mimicked an IAR filter design, but the poles are either at the origin or on the unit circle, which is basically trying to cancel a zero there, and the effect of the pole is lost in that process. Okay, so it is definitely good from all different perspectives. Good from the point of its reliability and robustness, the high accuracy it got, very neat algorithm, and it also has a very efficient hardware implementation. So this is why this work is very highly cited work in the research community, probably the most used biomedical algorithm out there, and it also has a commercial value attached to that. Okay? So I hope you can go through the paper, and you can also try to implement whatever we have discussed this in your lab experiment, which is basically going to be working on real world ECG signals applying the Pan-Tompkins algorithm there. And what other modifications we can do is that, I mean, heart rate, pretty easy to do. Once we detect the presence of the QRS, we can measure what's called the interval between the adjacent QRS pulses, which is also called the RR interval. And once we know the RR interval, then we could compute the heart rate in beats per minute, BPM beats per minute. That's how we mentioned the heart rate. So it's basically 60 divided by the RR interval in seconds will give you the beats per minute. Okay? And most of us, will have a heart rate on an average 70 to 80 beats per minute. Some people who are into extreme sports, athletes, they have a lower heart rate. People who are also into meditation and yoga will have a lower heart rate. When somebody tends to be stressed, obviously the heart rate tends to be slightly higher. And it's also possible, for example, if somebody is in a state of depression, the heart rate will be low. Okay? So the low heart rate, yes, we have seen that. I mean, you could say, okay, somebody is doing extreme exercise or yoga or meditation. It could also mean people are depressed. So that's why the heart rate is just a number which has to be seen over a longer time. Only when you see the heart rate over longer time, how it changes over time, that's where you can make a lot of interpretation out of it. And that's why we are also covering what's called HRV, heart rate variability is the key here. So rather than just looking into absolute heart rate, look into how the heart rate is changing over time. And HRV has a very significant connection, both in clinical application, also in wellness applications. Okay? And you can appreciate many of the wearable devices like the smart watches and the Fitbits and so forth are starting to give how the heart rate changes over time. And it is also obvious that heart rate for all of us changes over the day. And we also show a lot of heart rate variability during sleep. Okay? And we have actually in our research group, we have been working on heart rate variability and its effect on sleep. And this work has been going for the past 10 years in collaboration with the local hospital. And we are finding some very interesting observations in connecting heart rate variability with sleep. Now we are also starting to connect heart rate variability with the different emotional states, and that's an ongoing work, again in collaboration with a local hospital and industry. And by using the heart rate variability, which is again, if you plot the heart rate heart rate over time, like what's the beats per minute over time. So if this is the time, and if this is the heart rate on the y-axis in beats per minute, that's basically a plot of your heart rate variability. And this is, for example, where it shows your heart rate is changing over time. That's HRV signal. So now HRV, heart rate variability, has also become a time domain signal. Okay, just like how ECG is a signal, heart rate variability is in fact a time domain signal. Now from this time domain signal, we can extract features. So slowly you could see that we are moving towards the topic of feature extraction. So some common features we tend to extract from HRV is the standard deviation of RR intervals. Some people also call it as NN intervals. So interval between two RR peaks is also called NN. So it's a standard deviation. SDNN is one feature they extract. They extract the root mean square between the successive differences. So I would extract the differences between the two pulses, and I would do a root mean square of that. So that's RMSSD. Then you can do the standard deviation of that. And you could also extract the number of pairs of successive NNs that differ by more than 50 millisecond. Okay, because when you take the RR interval and if it differs by more than 50 millisecond, then you have to see how many of those successive pairs differ by 50 millisecond would give you another feature, NN50. So these features are well known in heart rate variability features, and we call them as handcrafted features, which is fed into an artificial intelligence model or a machine learning model to do a classification for us. So instead of really operating on this time domain signal, which I just showed you, we extract features like this, and the feature allows us to do a dimension reduction. And when we do a classification of this, then you can see the heart rate variability could be used for classifying whether a person is in different emotion state or if they're going through some clinical problems. It all could be classified depending on the context and the application that we wanted to use. Okay. In addition to time domain features, you can extract all other different variation of features. And in this course, we will see feature extraction, which is an important topic, and it's also an important topic for people who are doing project. Student B would be essentially be involved in the feature extraction aspect of it. So it's a broader topic, but slowly from this concept of filtering to heart rate estimation to heart rate variability, we will be migrating towards the concept of feature analysis. Finally, I really had the pleasure of meeting Professor Tompkins in a conference in July 2018. And at least, I got to mention to him that we use his algorithms, we teach his algorithms and techniques, and definitely he got to know about us as a Ryerson University and where it's located, what we are doing. And it was a very nice meeting with him because I've been following his algorithm for many years. And when we met in person, it was a very good chat with him. Okay, basically that's the talk around QRS complexes, and we will continue around this topic, especially around how do we do further feature extraction, because we can achieve quite a bit of success in monitoring this thing using advanced feature analysis and machine learning techniques.